So let's talk about this. Just to see if everybody is here. Here's what I'm going to ask. What this chapter is mainly talking about. So stars in general, uh, for the most part, work just like the sun. So everything we said about the sun last time, about how the core works, how fusion works, uh, how all the different layers of the star, all of that is roughly the same for different stars. But that doesn't mean all stars are exactly the same. There's a lot of properties that stars can have that can be different from one star to another. And that's basically what this final lecture is about. It's the differences between stars and how we figure them out. Because it's kind of difficult because stars are so far away. So here's the question I have. If we're looking at all these stars over there, just list off a bunch of things that can be different about different stars. What's different about different stars? What kinds of differences can these things have? Yep, I see somebody saying color. The color can be different. That's going to be one we'll talk about. Size can be different. That's another one. That's good. Give me some more. Give me some more. Distance can be definitely different. That is a difficult one. You can't actually see that, but that is something that can be different. That's true. So everything that you guys are saying are things that we're going to talk about in this chapter. Okay. Another one I don't think anybody's listed yet is brightness. Not all stars are the same brightness, right? And they can have different chemical makeups. Yes, you guys are basically hitting almost all of the ones we're going to be talking about. So let's talk about all of those different kinds of properties. And to do that, we're going to make two lists. Two lists of stellar properties, two lists of properties of the stars. And those properties are going to be divided into properties that we can directly figure out, essentially just by looking at the star, and properties that we can't directly figure out by looking at the star, properties that we have to indirectly find based on the information that we can see. So I'll be writing these down in a second, but essentially what I'm saying is this, is that some of the properties of the stars we can find by direct measurement. So for example, if I wanted to know how far apart my two hands were, you could put a ruler between them and directly measure the distance between my two hands, right? But my mass inside is not something you can see. That would be much more difficult to figure out. Okay, so let's do this. And I'm going to switch over real quick. Give me 1 second. So please write these along with me as we do this. So again, we're going to have one list called the direct list and one list called the indirect list. Oops. Indirect. We'll pretend that I write like a normal human being. So direct and indirect. And again, the ones that are direct are the ones that we can just measure with a device. Indirect is or another direct is we can measure with our eyes or with a device, and indirect we have to figure out from the stuff in the direct list. Okay, so here we go. It turns out the very first property that that you need to know before you can get any of the other ones right is the distance to a star. Okay? Because if you don't know the distance to a star, you're going to get almost everything else about it wrong. For example, if you don't know how far away a star is, you might be tricked into thinking it's brighter or dimmer than it actually is, right? Just as an example, or bigger or smaller, right? If something looks big to you, that either means it is big or it could just be really close, like up in your face, right? So let's figure this out. We're going to vote in the Discord, right? Vote in the Discord. The distance to a star, is that going to be something we can directly measure, or is it something we're going to have to figure out indirectly? So direct or indirect for distance. Indirect. Indirect. Now, normally we think of distance being something you can directly measure. Like if I wanted to know the distance between my hands, I just put a ruler between them. I could directly get that distance. But I can't do that for stars. Why can't we directly measure the distance to stars? There's a pretty simple reason for it. Exactly. Stars are just too far away. I mean, technically, if we had literally millions of years to do it, we could directly measure the distance, but because we don't have that kind of time, we have to indirectly find that distance. So let's put the distance over here. So distance is our first indirect property. And for each one of the things we put in this list, for most of the things we put in this list, we're also going to label them with a letter that represents that particular property. And so for distance, I'm going to just put in parentheses over here a lowercase d. That lowercase d will always represent distance. Okay. Now, how do we figure out the distance to the stars? There's not one method that always works, okay? There's not one single method that we use to find distance, but I'm only going to talk about one method for right now, okay? Now, check this out. Here we go. In order to find distance, the thing that we have to measure instead is called parallax. So I'm going to put that in the direct pile. Parallax. You might not have heard this word before. Okay, give me 1 second. There we go. Okay, just double checking. I am a terrible speller. I just wanted to make sure I spelled that correctly. Okay, now, looks like I got a couple of comments here. Okay. All right. And again, somebody's asking what's the direct and indirect. Remember, direct is things we can measure. Indirect is things we have to figure out. Okay? All right, so parallax, lowercase p. What is parallax? Parallax is a way for checking depth. Okay? It's a way for checking depth. And in order to understand it, it's really hard to put it into words. So we're gonna do a little experiment right now. Okay, it's experiment time. Let me move myself over here. Okay, now I should be roughly right in the middle of your screen. Okay, so here's what I'm gonna have you guys do. I need you to close one eye. Okay, close one eye. And while you have that eye closed, I need you to keep that eye closed. I want you to extend your arm fully out and cover my face up. And don't do it like this. It's not going to work if you do it like this. I need you to go full extension, okay? Full extension. Are you doing full extension? Are you covering my face? Do you have one eye closed? Okay, I'm trusting you guys. I trust that you got this set up. Do it full extension. Okay, here we go. Get ready. Here we go. Don't move. Switch eyes. Ha! Ha 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 ha! Did I move out from underneath your finger? A little tiny bit. Did you see my head look like it moved over a little bit? You weren't pressing my face anymore when you switched eyes. Okay? Should only move a little bit, but it should have moved. Okay? That's parallax. Okay? What just happened? You didn't actually move your finger, but because you viewed it from a different eye, your finger looked like it moved over. Okay? It's a little bit difficult to describe this online. But now, how does this help us? Okay, here's what I need you to do. Our experiment is not over, okay? So I need you to do the same exact thing. Close one eye, extend fully, and cover my face. Okay? And now what I need you to do, real quick, is switch back and forth between your two eyes and watch how your finger looks like it's moving. Watch it. Get a feel for it. Get a feel for it. Okay? Boom, boom, boom. I should be going in and out from behind your finger a little bit. Okay? Now, here we go. Here we go. Here's the final part of the experiment. Do this. Close one eye. Cover my face. But now, while covering my face, bring that finger a lot closer to your face. So cover my face with your finger close to your face. Okay? Now switch eyes back and forth. Whoa! Science in action! Whoa! What was different this time? What was different when you brought your finger closer to your face when you did that? What changed? What was different? I moved more. You saw more movement, right? Your finger looked like it moved much further off of my face. So that means when your finger was closer to your face, it looked like it moved more from your point of view, even though you know your finger wasn't actually moving. So that means, here we go, if your finger was closer to your face, did it have more or less parallax? When your finger was closer to your face, did it have more or less fake movement? More or less parallax? More, more, more. You guys are all getting it. This is correct. So, here we go. Let me move myself back. There we go. So what this means is that if we view a star from two different locations, in this case it was our two eyes, we could see the stars look like they move back and forth, right? And that means that the more parallax we see, the more fake motion we see, the closer that star is to us, okay? But we're not quite done with this, because check it out. If you were to go outside today and look at the stars with one eye and then the other eye, you're not going to see any parallax at all. Why would it be hard to see parallax on the stars? Yes. Yes. Good job. Good job. So essentially, remember we just said if something was close to you, it's going to have a lot of parallax. The stars are a ridiculous distance away, so they're going to barely have any parallax at all. So what we have to do in order to actually see parallax from the stars is not use our two eyes as our two viewing locations. Instead of using here and here, we can spread those viewing locations apart to amplify the parallax that we see. As long as we keep the locations the same for every star, we're going to get parallax that we can use to compare them, okay? Now, obviously, you don't want to take your eyes and put them apart, right? You want to keep those in your head. So what you can do is instead of viewing one eye and then the other, you can view a star from here and then here. And then you can see that that's like your left eye and your right eye. But that's not far enough apart. We need to get those viewing locations as far apart as possible, okay? And a lot of times when I ask this in class, I ask, okay, what's as far apart as we can get for these viewing locations? And people want to tell me on opposite sides of the Earth. It turns out that is not enough to see parallax on stars, okay? It's not enough. We need those viewing locations to be way farther apart than the width of the planet Earth. And so let's figure out what we can do. Let's figure out how this is going to work. How can we get our viewing locations way farther apart than opposite sides of the Earth without ever leaving Earth. Ooh. So someone's saying put probes in space. That would be better, but still not enough. How can we get our two viewing locations to be really far apart without ever leaving Earth? Here's a hint. You don't have to view the star at the exact same time from both viewing locations. Somebody said it in one of the classes. This is a little bit difficult, so I'm going to go ahead and explain this, but somebody got it. We use the orbit of the Earth itself. So check this out. I got a slide from the book. Here we go. If we look right here, come on, there we go. In this picture, imagine that we're looking at the stars up here. This is the sun. This is the Earth orbiting around the sun. If we were to view these stars in January, we would see that star from this angle in January. And if we wait half a year till July to look at the same star, it will look like it had moved over because we're viewing it from way over here now, okay? So in this picture, this would be like your left eye, this would be your right eye, and this would be like your finger in our little experiment. It's looking like it goes left and right as we move around the sun. So this is basically putting your two eyes on opposite sides of our orbit, and that's an extremely far distance apart. And even then, we still barely see any parallax at all. Almost all stars still show no parallax. Only the very closest stars would show parallax from this. And essentially what it would do is if we had if this was a picture we took in January, if we look really closely and take this picture again in July, almost all of the stars would be in the exact same spot, but say a couple of them, like this one, might move from here to here. Like from here to here. And I'm actually exaggerating how much you would actually see. Would this be easy to notice? Would it be easy for you to notice this happening? No. The only way to do it would be you'd have to take very precise pictures and compare them side to side, and you probably would have to get a computer to help you look for any slight changes in these things. So that means that parallax, the parallax method, is only going to work for what kind of stars? What kind of stars does the parallax method work for? Only stars that are something. Close. Only stars that are close. This only works out to maybe 1,000 or so light years, which is way bigger than our solar system, but it's nothing compared to the full size of the universe. So we have to use other methods to figure out the distance to the other stars. But for now, let's assume that for the rest of this discussion, we've used the parallax method or some other method to find the distance, okay?